So remember, this is where we kind of get into this idea of the student's T distribution, which looks a little bit different than normal distribution. Calculating your population mean, you can see is the same calculation as we did the point estimate. So you take your, whatever the parameter we are looking at and divide it by, your sample size. So this calculation is similar to our point estimate we did in section 9.1. This kind of shows you how, instead of using z-score, we actually end up using the t-score, or the t-value, which is very similar to a calculation for z-score. So you are taking, since we're talking in terms of a distribution for a sample mean here, you're taking the mean, which is from the samples, subtracting the population mean from it, but you will see we divide by standard deviation, which is actually using the standard deviation of the sample divided by your square root of n. So this is kind of where the calculation changes because we're finding the t-value. And then remember, we talked about with the t-value, you have to have a degree, oh my God, that term just completely flew out of my head. Really? Degrees of freedom, sorry. Oh my God. Degrees of freedom is what you need. And then of course you need to know what, the probability we are kind of considering over here. So you can see some of those properties here. Again, we kind of went over that last time, so I'm not gonna take time of that. But basically, as you can see, this is a little version of the table. You kind of have to look at the area on the right-hand side of the tail. So instead of left-hand side, which is what we do in the normal distribution, here it's going to be the right-hand side of your tail. And then you have to look at your degrees of freedom, which remember is n minus 1. So that n again is your sample size, and you do n minus 1 as the degrees of freedom calculation. So here you can see when we're building a confidence interval for the population mean, we are similar formula to what we saw in last section, but again, you're using the sample mean minus the t-value based on, again, alpha divided by 2. And then you can see our standard deviation here is based on the sample standard deviation s divided by the square root of n. Alrighty, so of course that means your margin of error is also calculated by that same factor that we saw for the confidence interval right here. And they had also actually talked about how you can pick your sample size, so how to calculate the sample size, and you will see that was based on this little formula over here. So let's take a look here. Yes, the other thing we had talked about was we will, it's okay to start using StatCrunch, basically starting with chapter 9, because for Excel, and I don't even know if this translates to Google Sheets, you will see for Excel, you have to download this add-in called Excel Stat. And when I tried downloading it, it was asking me for a paid subscription. So that's why if even students have to do that, I don't want you guys to have to pay anything additional. So that's why we're not going to be using Google Sheets or Excel on this, but you can start using StatCrunch and you can see the steps that are given to us over here for using StatCrunch. As you can see, this one is talking about blood alcohol concentration, for short BAC. So we're saying, okay, we have a random sample of 51 fatal crashes in 2013 in which the driver had a positive blood alcohol concentration from the National Highway Traffic Safety Administration results, and they had a mean BAC of 0.167 gram per deciliter with a standard deviation of 0.10 grams per deciliter. So they're saying a histogram of blood alcohol concentrations in fatal accidents shows that BACs are highly right skewed. So basically what this is telling us is the population from where we are getting our sample from is not normally distributed, right? Because it's telling us it's right skewed. Explain why a large sample size is needed to construct a confidence interval for the mean BAC of fatal crashes with a positive BAC. So this is something we did talk about last time in class, and the idea is as the sample size gets larger, your distribution starts looking more symmetric and bell-shaped. So you will see, there are actually a couple examples here in your textbook where they show you that comparison. So you will see on the left-hand side, we have this is a sample size of 5, and you can see when we increase the sample size to 10, how the histograms change shape from figure 9 to figure 10. And if you continue on, there was another example where they talked about how so basically, I think it was this little graph over here, figure 11. So you can see in number 6 as the property, it's telling you as the sample size n increases, the density of curve, density curve of T will get closer to the standard normal density curve, which basically means you are getting into that normal distribution shape. So that's kind of the explanation we need to do for part A, and I'll type one later. Let's look at part B here. In 2013, there were approximately 25,000 fatal crashes in which the driver had a positive BAC. Explain why this, along with the fact that the data were obtained using a simple random sample, satisfies the requirements for constructing a confidence interval. So you can again see they're kind of doing a little bit of those explanation examples over here. And basically, again, we can talk about how if you look at like some of the descriptions over here, you know, your area in your tails is a little bit greater than the area in the tails of a standard normal distribution. So this is where, again, we want to make sure we have a large sample size, and you will notice that there are some of those similar properties in terms of symmetry, where the area of your curve, under the entire curve is 1. To the left-hand side of the center is, where you can see 0 in figure 11. Left-hand side is 50% of your area, right-hand side is 50% of your area. So a lot of similar properties, between the standard normal distribution and then the t-distribution that we are talking here. And yeah, we also had talked about how you can either do a simple random sample or have a really large sample size for us to be able to use, the approximation that this will be normally distributed. Alrighty, so those are your kind of like theory questions to explain the reasonings behind it. Now you can see in part C, they are asking us to determine and interpret a 90% confidence interval for the mean BAC in fatal crashes in which the driver had a positive concentration. So this is where we bring in our little formulas. Just here, so yeah, you can see here is our confidence interval. So we need the sample mean, that's the X bar. We need to find our t-value based on alpha divided by 2, your standard deviation for the sample, and then of course our n value. So let's put all of those together. Okay, so we are actually doing part C right now. Since our confidence interval is 90%, we know as a decimal that's going to be 0.90. So anytime you need to calculate your alpha, remember alpha is 1 minus whatever is the value for your confidence interval. So 90%, which means 10% is going to be alpha, which as a decimal would be 0.10. And again, if you wanted to add an additional 0, again, you can do that. So remember, we have to do alpha divided by 2. So obviously that will be half of 10%, which will come out to be 5%, or as a decimal, 0.05. And then let's see, since we are doing 20% confidence. Oh, some of the other properties that we should be matching is also your sample size should be less than 5% of the population size, and then distribution table here. And so, while about other information we will have. So they're already telling us what the mean is based on our random sample of 51. So we already have the n value of 51 from our example here. So 51 random crashes that have a mean BAC of 0.16. So that will be our X bar value, since that's based on the sample. So 0.167 grams per deciliter. They're also giving us the standard deviation, so that would be the small letter s, which is 0.010. So we've got our n, x bar, s. Really, we just need the t-value based on alpha divided by 2. So let's go back to our table over here. And again, remember the table is available in the formula from the textbook handout. That's the very first one that you see. In, your D2L. Let's see. System distribution. And you can see there's our T distribution over here. So remember, we're talking about the area to the right-hand side of our tail. So remember, that's going to be that alpha divided by 2 value here, which is the 0.05. So that's what our alpha divided by 2 is. And then your degrees of freedom is what you need to do. So remember, degrees of freedom is n minus 1, which of course, as you can imagine, that's going to be 51 minus 1. So our degrees of freedom is going to be 50, which means we're going to be kind of at the bottom of the table. So again, the area was 0.05. So that's the area on the right-hand side. So 0.05 is right here. And then we need to keep going down for degrees of freedom of 50. And you can see that brings us at 1.1676. You guys can see that kind of at the bottom. So 1.676. And now you just have to put it all together in our little formula over here, which you can see again is kind of mentioned right here. So you are doing x bar minus the t value multiplied by standard deviation divided by the square root of n. So that will be our lower bound for the confidence interval. So x bar is our mean minus the t value multiplied the standard deviation and then divided by the square root of n. You can see what that number comes out to be, basically keeping the same exact formula, but instead of minus, we will be changing that to plus for our upper bound. So just change that. I'm still using all the right numbers here, so that should be good. So now they're asking for an interpretation. What is this confidence interval telling us? Interpretation of it. A little there. So this will actually round up to 0.165 and then this will be 0.16. Any ideas on how we would state the interpretation for what this confidence interval is telling us? Basically, we can say that we are 90% confidence because that's the 90% interval threshold that we had. So we can be 90% confident that the proportion of fatal crashes that happened in which the driver had a positive blood alcohol concentration will fall between a level of 0.165 grams per deciliter to 0.169 grams per deciliter. So that's kind of where your interpretation will come into play. And, of course, look at the examples in your textbook to see how they are writing it out. And you can kind of use that to transfer it to your example, which would be the best way to approach it. Any questions on part C over here, calculating the confidence interval? Okay, part D is saying all 50 states and the District of Columbia are a BAC of 0.08 grams per deciliter as the legal intoxication level. Is it possible that the mean BAC of all drivers involved in fatal accidents who are found to have positive BAC values is less than the legal intoxication level? Is it possible that the mean BAC of all drivers involved in fatal accidents, those who have a positive BAC value will be less than this level of 0.0? What do we think? Odds on that? Is it possible if you are involved in a fatal accident that the blood alcohol level, even though positive, was less than 0.08? Have any thoughts? Is it possible to have that level less than? Reason? Like why it's not going to be possible? What do you think on that? So this is kind of again something that we had talked about on Monday. So they're asking us, can we have a positive blood alcohol concentration value which will be less than 0.08, if the driver was involved in a fatal accident? So remember, in these calculations, we are using the sample mean, right? We're not using the population mean. Because we're using the X bar like we saw in part C calculation over here. So it is possible that the true mean from the population could be lower than this level of 0.08. But because in our calculations, we are using a sample mean, remember how with each sample that mean and standard deviation can keep changing, which is the reason why we kind of do these calculations over here. So yeah, it is possible that the mean for all drivers could be a value lower than, the legal limit of 0.08. Because, obviously we don't have the true mean for the population. So yeah, sometimes it may be hard to tell what we are looking at as the population mean. We're estimating them, but we don't know the true mean. That's kind of where we're. All right, perfect. Let's see. This is 2. Now you will see 9.3 really is just kind of putting it all together as it calls it. So it is basically taking that approach of, what are we doing to construct our confidence interval? You can kind of see the flow chart process over here. What parameter are we looking at? Are we looking at the population proportion, or are we looking at the population mean? And then you can see from there, it kind of takes you into the steps of what we would need to do. So honestly, this is just kind of putting the two things that we have done and putting it all together. So you can kind of see there's really not a whole lot of explanation over here, just an example to look at. So let's take a look at this guy. Which method do we use for constructing a confidence interval? And this kind of makes sense because when the problems are thrown at you, you wouldn't know if you're using the formulas from 9.1 or are using the formulas from 9.2. So here you can see they're talking about Robert wishes to estimate the mean number of miles that his Buick LaCrosse can be driven on a full tank of gas. He fills up his car with regular unleaded gasoline. from the same gas station 10 times and records the number of miles that he drives until the low tank indicator light comes on. So you can see that data in table 4 over here from his 10 different times that he tried that. And they're asking us to construct a confidence interval for the mean number of miles driven on a full tank of gas. So you can see they're asking us to build or construct a 95% confidence interval for the mean number of miles driven. So here we're going to treat our data, as you can see, as a simple random sample taken from a larger population. The sample size is small, which means we will need to verify that the data comes from a population that is normally distributed with no outliers. So remember, this is where we talk about, is our population size less than 5% of the sample size from the population size, and then I'm trying to see, talking about C figure 18. And of course, they're kind of guiding you to this flow chart also to kind of take a look at which direction we need to go. And then over here, they're kind of showing you what the plot for this data looks like. And then of course, the box plot over here. Also, they're showing you, is it symmetric? Is it kind of bell-shaped or not? And you can see in the box plot, definitely you can see there's a little bit of a slight skew on the right-hand side because that whisker is a little bit longer, but then the box itself, again, it does look slightly bigger on the right-hand side, but I would say it's probably not significantly out of shape per se. So basically they are using those and they're saying concluding the data can possibly come from, a population that is normally distributed. We're not seeing any outliers because you would have otherwise seen like extra dots on the outside of the box plot. So we did not do that. So we can say, yes, the population is approximately normally distributed. And so then, we can use those techniques to do this. So our sample size is 10 from the table that is given to us from the 10 rides this person did, we can get our mean and standard deviation from it. For the 95% confidence interval, we will need our degrees of freedom, which will be n-1, so 9. And you will see, since we are finding the mean for the rides that he's done, we are actually going with the t-distribution calculation here. So then based on that, you can come up with your confidence interval. And we are saying that, we can be 95% confident that the population mean for the miles driven on a full tank of gas can fall anywhere from 350.29 miles to 411.05 miles. So this section is basically just showing you, hey, which formula do I use? Do I use the population proportion calculation, or do I use the population mean calculation? Alrighty, guys, so that brings us to chapter 10. And this is where we kind of build up from what we talked about in terms of confidence interval, and we get into hypotheses testing over here. So hypotheses testing let's get into what exactly is hypothesis testing. So simple question here, they're asking us, is your friend cheating? So a friend of yours wants to play a simple coin flipping game. If the coin comes up heads, you win. If it comes up tails, your friend wins. So suppose the outcome of 5 plays of games is, you can see all of them came up to be tails. Well, is your friend cheating? So to decide whether your friend is cheating, we need to talk about, what is the chance that we would get 5 tails in a row? And, from that binomial experiment we had done, we know this has a very low chance over here, but we can calculate that. So we know the probability of getting a tail or a head is 50% or 1/2. We know each of the flip is independent. So is it unusual for 5 tails in a row on a fair coin? So basically we take that probability of 1/2 and multiply it into itself 5 times because we're repeating this experiment 5 times. And you can see that probability comes out to be 0.03125. So if a fair coin is flipped 5 times, so out of 100 different times, 3 of them should be where we get 5 tails in a row. So this is obviously not very likely. So you can either make the conclusion that your friend is not cheating and just happens to be lucky that, it's one of those 3 times out of 100 that, you land on 5 tails, or your friend is not using a fair coin. They're using a weighted coin where it purposefully lands on tails every time and they are cheating. So is your friend cheating, or did this just happen as an unusual result? This is kind of where we get into the idea of hypotheses testing. So we can make an assumption about reality, which in this case is that the probability of getting a tail is going to be 1/2. And then we look at or gather, they're saying, other sample evidence to determine if there's anything that can contradict our assumption. So this is basically what happens in hypotheses testing. So they're giving you a dictionary.com definition here that a hypothesis is a proposition which is assumed as a premise in an argument. So to suppose, as they're saying, from the Greek word that it originates from. So what is the definition of hypotheses when we're talking about statistics? Again, it's regarding a characteristic for one or more of our populations. So let's take a look at this example here. So according to a Gallup poll conducted in 2008, 80% of Americans felt satisfied with the way things were going in their personal life. A researcher wonders if the percentage of satisfied Americans is different today. So has that proportion changed basically from 80% to something else? So this is where, again, we were bringing hypotheses testing. The packaging on a light bulb states that the bulb will last 500 hours under normal use. A consumer advocate would like to know if the mean lifetime of a bulb is less than 500 hours. And they're kind of giving you what calculation we would have to use. You can see this one is talking about this is based on population proportion. The second one was based on population mean. Our next example is saying the standard deviation for a rate of return for a certain class of mutual funds, how much money you can earn on it, is at about 0.08%. A mutual fund manager believes the standard deviation of the rate of return for his fund is less than 0.08%. So here we're actually talking about based on standard deviation for the population. So like I said, all of these 3 are scenarios where we would consider using hypothesis testing. So that's a procedure where it's based on sample evidence and probability used to test statements regarding the characteristics, one or more for that population. So make a statement regarding the nature of the population, collect your evidence, which would be sample data, to test the statement, and then of course analyze the data so that we can assess the plausibility of that statement. Has that changed? Has the satisfaction of people changed with their lives? And, is the mean different, or that kind of thing? So here we're talking about using sample data to test our hypotheses. So again, remember, we're not going to be 100% certain if the statement is true. We can only say if our data supports the statement or not, because again, we cannot do this for the whole population. We can only do it for that sample that we are testing. So they are actually telling us, because the statement can either be true or false, hypotheses testing is based on this idea of 2 types of tests, and you can see those listed in the definition. So a null hypothesis, which we call it as H sub 0, the notation, or H naught, is a statement that needs to be tested. So that's kind of the statement we are making, that 80% of Americans are satisfied with their life, kind of thing, okay? The null hypothesis is a statement of no change, no effect, or no difference, and it is assumed to be true until we have evidence to prove it otherwise. Your alternative hypothesis, which is H sub 1 or H1, is where we're trying to find the evidence to support that there has been something that has changed. So we actually do this in three different ways when we're talking about null or alternative hypotheses testing. So you can see there will be a two-tailed test. So where we're saying a parameter is equal to some value or a parameter is not equal to some value. So we're not talking in terms of did it grow or did it go down or go up. We're just saying it was equal to this and now it's not equal to this. So that's your two-tailed test. If your alternative hypothesis is saying the parameter has dropped in value, then that's a left-tailed test. And of course, the right-tailed test would be if we're saying the value has gone up, so the parameter is now greater than some value. And you can see on the left-hand side where it's got the in other words description, the null hypothesis is a statement of status quo or no difference, and always contains a statement of equality. The null hypothesis is assumed to be true until we have evidence to prove that it's not true. And we seek that evidence, there's evidence that supports the statement in the alternative hypothesis. So we're trying to say, is the alternative hypothesis in fact true and our null hypothesis has changed? So since we are talking about two tails and left and right tails, of course, since you're only looking at either the left or the right tail, they can also be known as one-tailed tests. And you will, of course, see that we use less than or greater than symbols in those. They're kind of breaking down the different examples we saw on the previous page. So again, instead of me reading through that, I'd ask you guys to read through that description yourself, but let's look at this example here on how we can come up with our statements. So they're asking us to determine what the null and alternative hypotheses should be and whether it should be a two-tailed or one-tailed test, or left or right. So the Medco pharmaceutical company has just developed a new antibiotic for children. 2% of children taking competing antibiotics experience headaches. As a side effect, a researcher for the Food and Drug Administration wishes to know if the percentage of children taking the new antibiotic who experience headaches as a side effect is more than 2%. So if you look at the part A of the solution there, we're saying, okay, so we are obviously dealing with a population proportion because we're talking about the number of children, right, as a percentage who are having headaches as a side effect. So that's going to be P. If the new drug is no different from the competing drug, then the proportion of individuals taking the headaches will stay at 0.02, right? The 2%. So your null hypothesis, as you can see over here, is that H naught with the sub-zero is going to be our population proportion, P equal to 0.02. So what will the alternative hypothesis look like? So remember, the researcher wants to know if the side effect is more than 2% for these children taking this medicine. So we want to determine if the proportion of individuals who have a headache is going to be greater than. So you can see in the alternative hypothesis H1, it's actually going to be P greater than 0.02, right? So since we're using the greater than symbol because it's more than 2%, that's going to be a right-tailed test. So one-sided. Part B is talking about the blue book price of a used 3-year-old Chevy Corvette ZR1 is $86,012. Grant wonders if the mean price of a used 3-year-old Chevy Corvette in Miami metropolitan area is different from $86,012. So you can see here, we are talking about the mean price here, right? We're not talking in terms of a population proportion this time. We're talking in terms of a population mean. So you will see we are actually using the mu symbol in this example. The other keyword you should notice is they use the term different. They didn't say greater than, less than, more than, less than, any of that, right? They said different. So this actually tells you this is going to be a two-tailed test. Because we don't know if it's above or below the mean price. We just want to know if it's different. So for your null hypothesis for this example, you will see it's set at that mean price of $86,012. Grant wanted to know if the price is different, so you will see for the null hypotheses, we are using the not equal to sign because we just want to know if it's different. So that makes it a two-tailed test instead of just a one-tail. And then part C here was talking about the standard deviation of the contents in a 64-ounce bottle of detergent using an old filling machine is 0.23 ounce. So the manufacturer wants to know if a new filling machine has less variability, which means will it be more accurate, right? So they're talking about less variability over here. Of course, they were talking about standard deviation. So we are talking about sigma. So your null hypothesis would be, okay, so the older machine had a standard deviation of 0.23 ounce, the filling machine. And they want to know if the new machine will have less variability. So you can see how the alternative hypothesis is sigma less than 0.23. So as you can see, this will be a left test, tailed test for the hypothesis testing. So 3 different types of tests that we do: two-tailed, left-tailed, right-tailed, and how we come up with those. But also, what do our outcomes look like when we actually do the hypotheses testing? So they're saying sample data, again, is used to decide whether or not we keep the hypothesis testing or we reject, do we keep the null hypothesis or do we reject it? Because this decision is based on sample data, we can think of that as incomplete information. There is a possibility of us making an incorrect decision because, again, we don't have all the information. So here they're listing what those 4 types of possible outcomes from a hypothesis testing could be. So you reject the null hypothesis when the alternative hypothesis is true, which makes sense because we're saying the null hypothesis is not true anymore. The alternative is true. We have enough evidence to prove that. So you will reject the null hypothesis and accept the new one. So this is where our decision was correct of rejecting the null and accepting the alternative. We do not reject the null, even though the null hypothesis is, we do not reject the null hypothesis when the null hypothesis is true, which makes sense. If the null hypothesis is true, the alternative hypothesis did not prove that it was true, which means we keep the original value, which means we do not reject the null hypothesis. So again, that would be correct because null hypothesis was true. We kept that argument as it is. Now, we reject the null hypothesis when the null hypothesis was true. So our original value was true, but we rejected it. Obviously, that means we have made an error that would be incorrect, and this is what we call as a type 1 error. So now we're saying the null hypothesis was true, but we still rejected it. Type 1 error. We do not reject the null hypothesis, even though the second one, the alternative, got proven to be true. So we said that our alternative value was true, but we still do not reject the null hypothesis. So again, that would be an error, and that is where we call it a type 2 error. So this table or the box would be another thing I'd ask you guys to keep handy because it kind of tells you, what was the reality, what was the conclusion, and then based on that, we can say, did we do the right thing or did we make an error and it was a type 1 or type 2 error? And then they're again kind of going into a little bit of an explanation of kind of using those, but again, I'm going to jump to our example here. So kind of going back to that Medco example. So they've developed a new antibiotic. 2% of children are experiencing headaches as a side effect. And the Food and Drug Administration wanted to know, is that number larger than 2%? So as we saw, our null hypothesis would be probability proportion. So P equals 0.02, which is what the pharmaceutical company is saying. But the FDA researcher wants to know, is that number larger than 2%? So that's where that alternative hypothesis of P greater than 0.02 is coming into place. So they want to know, would it make it a type 1 or a type 2 error? So remember, type 1 is where even though the null hypothesis was true, we rejected it. Type 2 error is where the alternative hypothesis was true, but we did not reject the null hypothesis. So type 1 error is made if the sample evidence leads the researcher to believe that yes, the probability is larger than 2%. That means we should be rejecting, the null hypotheses. So again, we're saying the sample evidence leads the researcher to believe that the probability is larger than 2. That is, we are rejecting the null hypothesis, when in fact, the proportion of children who are experiencing the headache is not greater than 0.02. So we're basically saying the null hypothesis was true, but you still rejected, right? Type 1 error. Type 2 error, we're saying the researcher does not reject the null hypothesis, when in fact, the proportion of children who are experiencing headaches as a side effect was more than 0.02. So this is where we're saying, yes, we're able to prove that more than 2% of the children are experiencing headaches, but they still did not reject the null hypothesis. So that is your type 2 error. So just an explanation of how to interpret when a type 1 and when a type 2 error is made. Yeah, this is where we actually talk about what is the probability that we will make, a type 1 or a type 2 error. So kind of think about how we were talking about margin of errors in confidence intervals. So here we're saying we only know the likelihood that a confidence interval captures the parameter. So in that same way, we can know whether a conclusion of a hypothesis testing is going to be correct or not. So just as we place a level of confidence in the construction of a confidence interval, we can also assign probabilities to type 1 or type 2 errors. And you can see the notations that we use here are alpha and beta. Alpha will be for the probability of creating a type 1 error. Beta would be for creating a type 2 error, and then they're just kind of breaking down the explanation for that. So same thing, level of significance, alpha, is that probability of making a type 1 error. And again, you can see they kind of break it down into a little bit more description of, that significance level. Okay, so we're talking about, let's say your level of significance is small, such as 0.01 over here. But if the consequences are not severe, we're saying a higher level of significance can be chosen, like, 5% or maybe even up to 10%. So why are we not setting that margin of error or probability of an error, sorry, in this case at 0.01? Because, if you can think back to how we were talking about margin of errors with the confidence intervals, reducing the probability of making a type 1 error will actually increase the probability of making a type 2 error. So they're basically saying, and I know I kind of skipped that court analogy, but a jury is instructed that the prosecution must provide proof of guilt beyond all reasonable doubt. So this implies that we are choosing to make a small type 1 error so that the probability of convicting an innocent person is very small. So the consequence of a small alpha value is going to be that you will end up in a large beta value, which means that many guilty defendants can also go free. So I guess what we need to remember is that the two values have an inverse relationship with each other. If alpha goes down, B will go up, or beta. If beta goes down, then alpha will go up. So that's kind of how these two will play off against each other, and we'll talk about that. So let's take a look here at how do we state the conclusions, and again, they're giving you a little bit of a paragraph. But going back to our Medco example, so again, new antibiotic, 2% of children are experiencing headaches. FDA researcher wants to know if it should be more than 2%. So suppose that the sample evidence indicates that the null hypothesis is rejected, how would we actually